Very good. You know, my interpretation of the title is telling you about BSM's physics, and it is 2026. I'm trying to give you timeless principles, which I believe are still active. I continue to work on them. They're very active on the experimental front. But there are new tricks coming up. I myself work on new tricks in this game, but there's not time in these introductory lectures to sort of go down those nuanced paths. That would be for another time. Very good. So, so last time, we followed what I called option one. We threw away the Higgs, looked at the nice structure of the Standard Model without the Higgs as a chiral gauge theory and said, look, it's a massless theory, which is at least on this linear scale, a pretty good approximation to the truth. So maybe that's the 0th order step. And then we put in non-perturbative effects, in this case from QCD, and we found, if you now resolve things on a logarithmic scale, you can start to see interesting structure. With one generation, we managed to get some sort of heavy fermion, we could call it top quarks, as well as light electrons, sort of Higgs in the form of the mesonic sigma resonance, and the W's and the Z's getting mass by eating pions. So it started to look a little bit more realistic, but of course, I emphasize, this is a toy model. Don't take it too seriously. Look for the principle that will allow us to go to a realistic model. In particular, I'm selling this aspect of quantum field theory. So of course, it was unrealistic. It only had one generation. The weak scale, actually, the W's and Z's are around 100 MeV. So the question that was asked yesterday, whether the sigma resonance, the mesonic Higgs that QCD supplies us with, would it be narrow like the Higgs we observe or broad? And the answer is conclusively broad. I should have said that. So yesterday I said it depends a little bit on the choice of electroweak couplings. Unless they're very strong, which they're not, this will be a broad resonance. Anyway, so it doesn't look exactly in detail like the Standard Model Higgs. And of course, everything is happening. It's one generation. This is not the real world. But it's striking. Okay, I'm introducing the idea of playing with toy models when you're dealing with conceptually tough problems. So I want to go to the real world today by introducing SUSY as the fastest path to a more realistic structure. We could go without SUSY, and there are some references in the lectures from 4 years ago that you can look at. But in these lectures, I'd like to go to SUSY. And so what I'd like to do is actually follow what I call option two, which is don't remove the Higgs, but introduce a symmetry so powerful that even the Higgs mass term, right, whether it's tachyonic or non-tachyonic, is forbidden or controlled by a symmetry, okay? And the symmetries we have are already the gauge symmetries of the Standard Model that you know, the chiral symmetries of the Standard Model that you know, as well as supersymmetry. So we're gonna shift to the MSSM. And we're going to have a set of symmetries which gives us this cartoon. Even with an elementary Higgs, it's going to give us this cartoon where the MSSM is completely massless, at least perturbatively, completely massless in this setting. And again, we're going to invoke a kind of non-perturbed, well, we're going to invoke these kind of effects, but not coming from QCD, but coming from some BSM strongly coupled theory, okay? And what it's going to do, okay, this is a cartoon. It's going to split things so that we are now really operating where we want to be, since it's a stronger force, or it has a higher lambda QCD, has a higher characteristic scale of strong interactions. It will allow us to live at higher energies in this sense. And instead of being sort of cartoons of what we want, you know, it will be the Standard Model that we get out with electroweak symmetry breaking. And there will be some breaking of the supersymmetry, because actually this is not a symmetry an experimentalist today can say, I've discovered it, right? So it must be broken in some way. And the same effects, just like QCD breaks chiral symmetry and electroweak symmetry, as we saw yesterday, the effects that we're going to talk about will break supersymmetry as well as electroweak symmetry, and there will be superpartners. So now, at the level of these lectures, I'm not going to agonize over why the LHC has not seen these yet, because I'm doing things at this level of accuracy, right? And that's the wisdom of the world currently. We understand qualitatively how this beautiful picture can emerge, right? But order 1 numbers and why things didn't show up as soon as they could have shown up, et cetera, I don't know. In a sense, we are operating between electroweak scale of 100 or hundreds of GeV as a sort of natural place something interesting might have happened to explain the hierarchical structure that we are seeing. And we have searches for superpartners that extend to roughly around 2 TeV, between 2 and 3 TeV, depending on exactly what the spectrum of superpartners is. So we're within the decade of sort of where we would have expected interesting things to happen. But there is no tight logic. There's loose naturalness, estimates, back of the envelope, as to where something should appear. But we are operating on a vast canvas. And experiments are operating sort of logarithmic down here. And I just don't know, okay? But there are lots of ideas, but I'm not going, on this level of detail, factors of 10, but not in these lectures, okay? You can ask me about those afterwards. I think the case is so compelling that I'm giving these lectures. So, and for what it matters, you always have to psychoanalyze anybody talking to you, like what's their agenda. And I just want to say, my reputation was not primarily based on supersymmetry. Okay, so I don't have some big axe to grind in that way. I have contributed to the subject, but I hope I'm being neutral in telling you that I think it is important that you understand this physics. And behind the supersymmetry, it's something that I feel even more strongly about, which is that non-perturbative effects can be playing a central role beyond the standard model. And therefore, you must take some pains to learn some of that. Okay, so let's use supersymmetry. So let's look at one particle states. When I talked about the entire Hilbert space of the harmonic oscillators, I was talking about any number of occupation number. Here, let's just look at one particle states in real quantum field theory. And they could either be bosons, so one boson, or it could be one fermion. Right? And we're going to generalize what happened with supersymmetry and quantum mechanics. And so we want, so we're expecting that there is a symmetry that makes this exchange, supersymmetry, that acting on a boson state creates a fermion and vice versa. But we know that there's a spin statistics connection, so that these things have to be half-odd integer spins, and this has to be integer spins. So this Q cannot just be a scalar. It must carry some half-odd integer spin index, right? So that I can convert something with integer spin into half-odd integer. So secretly, it must carry some sort of spinor index like this, okay? And it really, for the purposes at hand, better be, we can guess, it has to be a spin half index, because a spin half index could, for example, take scalars, such as we find in the standard model, to spin half particles in the standard model. I don't want some spin 5/2 index, which takes, say, spin 0 in the standard model to spin 5/2, right? No, that's not something in a renormalizable field theory that we'd ever play with, right? So it should be a spin half thing that can then connect the spins of renormalizable field theory at least, right? Spins, just these spins. So it can either go from here down to here, or here up to here, or here down to, right? So spin half. Okay, so this is a spin half index. So what we're going to see is that, so I should say, first of all, then what is the SUSY algorithm? It used to be very simple. Q squared equals the Hamiltonian. So we just need to generalize that. Now the Hamiltonian in a Lorentz invariant theory is a 4-vector. It comes with all of energy and momentum. And here we have this thing. Now, the fact that it's a spinner will automatically mean it's in the simplest representation, the sort of left-handed representation, two-component spinner, then it should be some sort of spinner, because it's a complex representation under SL2C. So there's not only this, there's going to have to be its Hermitian conjugate, which is just the bar. Okay, so there's these two kinds of supercharges. You can add them and get something Hermitian if you feel like. Okay. I do want to dot it if I were speaking very, very carefully. But as I said in my lectures last time, I'm not going to dot it just so that I'm not raising a different level of complexity. I will use it correctly as if it was dotted. But yes, it does not transform. So it's the conjugate representation to this. Okay, so I'm going to let you guys look at references or the way that I try to carefully not dot things, but do everything right in the written version. Okay, so in a sloppy way, this is it. Okay. The dotting, undotting, everything like that is really based on this particular generalization of q squared equals Hamiltonian. So this is like the q squared or anti-commutator of q with itself, but now with the barred guy with the unbarred guy. And I need to get something, but I need to get 4 momentum out. I can't just have the Hamiltonian sitting in a Lorentz covariant statement by itself, okay? And so the right thing that should go with it is something that connects all these indices, and it's basically what I'll call a chiral Dirac matrix, okay? Where if you're in the Weil basis, the Dirac matrices look like sigma mu, they're off diagonal. Where these are just this is sigma 0 is just the identity, and these are just the Pauli matrices, and here it's just the identity again, or minus the Pauli matrices. Okay, so this is just the standard Weil basis, but we're at 2-component levels, so this is sort of the chiral left-handed Dirac matrix, if you like, and that's what's hooking up all these indices and correctly treating this as a dotted index for those who keep track of that level, okay? Good. So this is the generalization of the SUSY algebra, and I should say going along with it is Q, the Q's themselves, not QQ dagger or QQ bar. Again, the bar is the same as dagger. These vanish. And I came at it from a very different, but I think very interesting way in the way I wrote things up. But this is the SUSY algebra. Okay, so if you want, this is it's q squared equals h that we're generalizing. Okay, now the amazing thing about the SUSY algebra is that instead of just working at the level of quantum mechanics, it works at the level of, so it's consistent with renormalizable quantum field theory. Okay. Now, as we're all effective field theorists, and so we know that effective field theories have utility and match data, and renormalizable theories have utility and match data, we should say, what is the difference primarily? Now, there's a technical difference, which I have to leave to you to look at other TASI lectures to recall or learn in your own grad schools. But ask me after. But morally, a renormalizable theory, a non-renormalizable theory has some sort of coupling with negative mass dimension or something, let's say like G Fermi in the 4 Fermi theory, right? And so the dimensionless strength of these interactions, like how important are these interactions, is given by something that balances the dimensions, so positive powers of energy and momenta, right? So if I go to very high energies, then this will become much bigger than 1. And perturbatively, at least, the theory makes no sense. And often, it just makes no sense and must be replaced by some UV completion. Standard model replaces this at energies where this is much bigger than 1, okay? On the other hand, at energies much less than 1, this is very small. Who cares? It's small. Forget about it. And that's basically the truth. Non-renormalizable theories are important. They do their thing in some range of energies of order a decade or so around the characteristic scale. Yes, very small effects can be very important if you have a lever arm like the muon would not decay at piddling energies of order 100 MeV, even though the characteristic scale of the non-normalizable interactions are 100 GeV. It wouldn't even decay if it were not for the weak interactions. So wait long enough, we become sensitive to weak effects. Don't worry about all of those lever arms. Basically, non-normalizable theories are sort of doing important things over a decade of energies or so, at best. Whereas a normalizable theory, where you have a coupling constant, which may run, but it varies sort of glacially over decades of energy, is important over large hierarchies, okay? So this is consistent with something interesting. SUSY is consistent with something interesting ticking away, doing interesting things for large hierarchies. This is morally how we should keep track of the significance of these two types of theories. Both have importance, but this is the difference. Okay. So extra-dimensional theories are more like this, as we saw. They're non-normalizable. They're interesting in some range of energies. Okay. So how does this extend to the standard model? So let me here write the standard model states that we know, and here write sort of who they partner up with. It would have been very elegant if the standard model states already came as bosons. After all, they do come with bosons and fermions, and they already paired up in the sense that nobody has found. I don't think it exists. That does not exist. We do not have a version of the world in which supersymmetry can pair up the bosons and the fermions of the standard model as relating to each other under the action of these Qs. Not true. So in the standard model thing here, we can have our cuddle again. 3 generations of this. This is conjugated, of course. So you know what I mean. And their superpartners are just going to be, so these are spin half. So at best, these Qs can take me to spin 0 or spin 1. But well, let's try spin 0 for a second. Sorry, they can take me to spin 0 or spin 1. We can try spin 0, which is the correct answer. And it gives a bunch of scalar fields, or spin 0 particles, which are just sort of cuddle tilde. Okay? And so these are the squarks and sleptons of supersymmetry. You could have said, well, why couldn't they take them to spin 1? And a priori, they could have taken it, a spin half operator, the Q alphas, could have taken it to spin 1. But then you would have spin 1 particles in fundamental representations of groups like SU3, like a color triplet gauge boson, okay? And so as you know, the only consistent theories of gauge bosons are gauge bosons in the adjoint representation of the gauge group, right? Not fundamental representation. So with a little detective work of this sort, this was really the only option. And of course, it is the textbook option. Then there are the gauge bosons of the standard model, which are the hypercharged gauge boson. I'll just write it like that. The W bosons before they mix with this and turn into the Z. They have some index there, right? 2, 3. And the gluons, which I won't have opportunity to write many times. I'll just write it as an A with joint index 8. There are 8 of these guys, right? Gluons, and their superpartners are sort of casual mention in Feynman diagrams are either the B goes to the BNO, the W goes to the WENO, and this thing goes to the gluino. But when you're writing them in, BNO, WENO, gluino. Anyway, I think the names are sort of probably part of popular culture, so you know them. And indeed, here we are going from spin 1. We definitely don't want to go to spin 3 halves. Again, in quantum field theory, those cannot be anything but a very, very special particle called the gravitino, which I'll mention in a second. There certainly can't be this many of them. So they go to spin half. So these are spin half, and these are spin 0. Okay, and typographically in equations, these are usually called lambdas. And again, usually lambda of U1, lambda of SU2, or lambda of SU3. And they're spin half, so they do carry this left-handed spinor index. And then we come to the Higgs. And so as spin 0, the only thing it could go to is a Higgsino. So you see the tilde-ing is sort of just a simple way of referring to the superpartner of the appropriate untilted guy on this side. So there's the Higgsino. Now we hit a problem. We think it's a two-component, right? Spinor, left-handed spinor guy. But if you add this to this list of fermions that we have here and here, if you add this, the theory has gauge anomalies. I think it has the hypercharge anomaly is also uncanceled by just doing this. And on top of that, the Witten anomaly, the one I was talking about, the non-perturbative anomaly that Witten discovered, which is what's also called a global anomaly, you suffer from that. So this theory, as I've written it, by sort of supersymmetrizing in this way, is inconsistent because it's anomalous. So the best you can do is to add this and a different Higgs, which has exactly the conjugate. So if you think of this as left-handed, think of this as right-handed, so that anomalies cancel trivially. If I then turn this into a left-handed field by charge conjugation, I just mean that this second Higgs has to have the conjugate quantum numbers to the first Higgs, okay? Higgsino's, if you want. The Higgsino's should be conjugate. But then I have to go back because I have supersymmetry, so I should actually have a second Higgs, right? I should actually have a second Higgs, if you want, let me call it 2. I should have a Higgs boson to go along with my second Higgsino. So in fact, we must be in a 2 Higgs doublet standard model, okay, plus its superpartners. So this we can deduce sort of on just like, if this is going to get anywhere, if we're going to be able to get away with it, it must look like this minimally. And so let's go with that. Just as a final word on this spin 3/2 case and so on. Of course, we also have gravity. So should I? I guess it's poor form to write there, huh? Well, I'll do it anyway. I have poor form. Oh, yeah, question. No. Here, here it went up. Yeah. So in fact, I'm claiming that these, whether it went up or down, was like we could deduce it almost from just getting something that could possibly sit in a renormalizable Lagrangian. Like as I said, there are no renormalizable Lagrangians where I go to spin 3/2, and there are even other problems if there are too many spin 3/2 particles that are. So it's a matter of consistency that this is the only consistent option. Yes. I mean, of course, you could say, well, why do I have to do Higgs doublets? Maybe I could do Higgs triplets and so on. So yes, there is an anomaly cancellation requirement. If you only stick to doublets, it must be even numbers. Yeah. Okay.
What are the 1 and 2 superscripts for the Higgs?
These ones? Yeah, so I just said that for anomaly cancellation reasons, we can deduce that we must have pairs of Higgs doublets. So I'm just calling them 1 and 2. We'll give them a better name in a second. But right now, it's just counting, so I call them. No. So maybe if you want, let me just call it H and H prime, and let me call it H and H prime, just to avoid confusion. Okay, so indeed, there is the graviton here. Okay, sorry. I want to get it all on one board. There is the spin 2 graviton of the real world that's holding you to the ground, at least virtually. And so there should be something here. Again, it's spin 2. massless, spin 2. And remember, these states are, with supersymmetry intact, these states would be degenerate, okay? Because the q squareds, or these things commute with the Hamiltonian. So they would prove that there was degeneracy. That's not a, of course, we haven't seen a particle like this with charge -1 or 1, which is degenerate with the electron. So we know supersymmetry is broken, but we know that's coming. That'll come. But at this level, it would be degenerate. So we'd have to have something degenerate with a massless graviton, which would be a massless either spin 3 halves or 5 halves. Now, Weinberg has effectively shown that any spin higher than 2 cannot be massless in an interacting theory. So that's that out. So it's got to be spin 3 halves. So it's the spin 3 halves. So this is spin half. And this is the spin 3 halves. And you'd say it's the gravitino. Okay. Now, the amazing thing is that gravity is basically gauging energy and momentum, right? The charges of gravity are energy and momentum. So if this is being gauged, and this is the algebra, you may well conclude that something should be gauging this. The whole thing should be gauged. These are not global symmetries. There actually should be gauge symmetries fundamentally. And indeed, that's what this gravitino is for. In fact, it is really the gauge boson, but it's not a boson. It's the gauge fermion associated to supersymmetry. This is the charge that the gravitino thinks is its gauge charge. And combined, if you think of this as, it's an anti-commuting thing or a graded algebra. But this sort of non-abelian structure really says that gravity and this supersymmetry form a single structure, which is a kind of non-abelian gauge theory, which involves both gravity translations and super translations or supercharge. And so the whole thing as a gauge structure is called supergravity, or affectionately sugra for short. Okay. So as long as you're not worried about gravity level precision, like most of what happens in the lab, right? You can just think of it all as global symmetries, and translation invariance is a global symmetry. But secretly, this was what's going on. Okay. And this was, in fact, the direction that I approached the entire subject in the notes. So you'll see an orthogonal way, which I think is very beautiful for coming at supersymmetry. This is the only other gauge force, according to Weinberg's analysis, that there's no sort of massless spins higher than 5, higher than 2. We have gauge forces with spin 1 carriers, gauge forces or gauge structure with spin 2, and gravity is a unique allowed thing, general relativity. And this would be the only other kind of gauge particle or gauge theory that is allowed consistently in a Lorentz invariant universe. Completes all, if this was there in nature, if this is there in nature, this would be nature playing every trick in the gauge theory book that is allowed, okay? Yeah.
Is there a simple way to see that Weinberg's argument that there could be massive particles?
There is, I tried to write it out.
Raman?
Yeah,
Could you
yeah, so the question is, this intriguing statement I made that Weinberg has shown that you can't have higher spin massless particles than 2, right? And a number of other seemingly very powerful statements where you don't need to go and check with experiment to know what can't happen. The taste of them is rather simple, and I've actually lectured like that in the 2022 lectures that are parallel to this, and I think it's in the write-up, but will take us a little. I don't have a one-line answer, but it is simple enough that you would enjoy reading that or seeing my lecture online. Yeah, so it is worth understanding because it's so cool to see. Is nature just doing everything it can do? Once you give me Lorentz invariance, is it just playing every trick? Or is it like picking and choosing? And I would argue, my sense is that nature is playing like every trick because there are so few tricks. And it doesn't seem to be very stingy with what it does. Yeah.
Isn't say gravity as the gauge chart or
The gauge force carry. It's not a force because it's not a, it's a gauge field, but it's not a gauge boson because of the funny nature of supersymmetry.
doesn't it put it on a special footing?
It's on a very special footing. It's the only gauge field that doesn't have to be a gauge boson.
Yeah. So is it like a more EFT way of thinking about things where on a more fundamental level everything would be I know I'm sounding very vague, but I don't know what the question is.
Yes, so again, this is the way I have written things up in the 2022 case, is to think that the right way of thinking about supersymmetry, or the elegant way of thinking about supersymmetry, is as an extra-dimensional theory, right, where the extra dimensions happen to be Grassmann numbers rather than ordinary numbers. So then, I think I'm quoting John Bagger in saying this, that the idea is to view supersymmetric theories not as extraordinary theories in Minkowski spacetime, as boring average theories living in superspacetime. Okay, and so indeed the gravitational field in superspace, if you expand it out, like you do the analog of the Kaluza-Klein expansion for bosonic extra dimensions, but you do it for fermionic extra dimensions, then you'll find that some of the fields, the component fields, are the metric, and some of them are the gravitino. So there is a way of sort of unifying it and saying there's only sort of fewer moving parts. But okay, let me keep going because I need to give you guys punchlines. But I'm happy to answer all these kind of questions too over coffee or whatever. There are many such interesting questions that one can ask. It's such a beautiful subject, theoretically. Good. So I want to write a Lagrangian for renormalizable. So I'm writing renormalizable SUSY quantum field theory. Again, a little more detail and coming at it from the superspace point of view and so on. It was done in the last TASI lectures. So here, let me just, however, write the Lagrangian. So first of all, let me write what would be the analog of harmonic oscillators without any interactions at the level of quantum field theory. They're called free fields, okay? And so here, and let me not worry about gauge theory structure. So let's forget about the gauge structure of the standard model. Let's just stick to the scalars and the fermions side, okay? So already I've written a covariant derivative, but let me explain. So there are some bunch, I'm not sticking to the standard model, I'm just writing renormalizable quantum field theory in general, okay? So there are some scalar fields, I'm calling them phi I, the scalar fields. And I've written covariant derivatives because I'm going to talk about gauge structure after I don't talk about it. So I don't want to write it twice. So just pretend for the moment that these are partial derivatives and not covariant derivatives. There is no gauge structure yet, okay? So anyway, there's some free fields like this, and there are the superpartners of these scalars, which are given by the Dirac, the chiral, the two-component version of the Dirac action, right? Okay, and I have several oscillators, several species of particles. That's all the I is. So there's this. Now, this is avoidable, but let me just say it because it's the language that is typically used, and it's the one that comes out of superspace. But I'm going to add a funny field. So this, you should not be surprised, right? This is like the A's and this is like the B's of my quantum mechanics example. The A's are when you turn field theory into a harmonic oscillator is one for every momentum mode. That is this theory here. And this is the fermions that go along with it under supersymmetry. But I'm going to add another kind of bosonic field, F, which doesn't actually have a kinetic term. It seems to only have some big mass term or something, right? So I'm going to write this as well. Again, it's avoidable, but it's part of the standard nomenclature. And so what we call the superfield, and this particular type of superfield is usually called a chiral superfield, and it'll indeed house, in the end, all the chiral fermions of the standard model. The chiral superfield is to be thought of as the collection of these fields, the scalar fields, which I'm writing as lower phi rather than capital Phi, the fermionic field, and this seemingly rather, it doesn't have a kinetic term. It only so it's what's called an auxiliary field. But it's usually put in here, and it's there just because it simplifies the supersymmetry algebra, which I'm not going to be, having shown you the quantum mechanics case, I don't want to overdo that here, but it is in the write-up from 2022 in a gentle introduction, so you can see how that goes. So this is the chiral superfield, and we'll see what purpose this plays, but this we sort of anticipated, okay? Now, you'll see that this is like the harmonic oscillator, the non-anharmonic, meaning the harmonic oscillator, meaning it's not that exciting. If you think of these as ordinary derivatives, then there are just no interactions in this theory. So we will want something like the analog of our anharmonic oscillator. And indeed, let me write it here, that we need the analog of the superpotential that we had in the harmonic oscillator. And indeed, it's called superpotential here too. So in order to write interactions, we're going to need a superpotential, okay, which is a superpotential, which is a function. Remember, before it was a function of the q's. Now the q's, so here too, it's actually going to be a function of really just this lowercase phi. Operationally, it's going to be like the quantum mechanics example, but it's usually written, again, because of superspace, which I'm not, it's optional, and I'm not forcing you to think about it right now. Read about it in my lectures. It's usually written as a function of the superfield, okay? But think of that as a formality. What it really is, so I'll put this in quotes, but what I really want you to think about is, so again, it depends on all these fields, is a function of the scalar fields. It's a function of the q's of the quantum mechanics theory, just like it was in my quantum mechanics example. But here's the thing. These phis, just like these chiral fermions here, are complex, okay? So these are, that's why the absolute values are there. These are complex. So when I write this, you could say, oh, so it depends on the real and imaginary parts of phi. Another way of saying that is, if it was a general function, you could say it depend on phi, the complex field phi, and its complex conjugate. That would be a general function, right? Now, you cannot see this in the quantum mechanics example, so I'm just going to tell you. You can see it if you read lectures. It's completely explained. That the superpotential, in order to describe four-dimensional Lorentz invariant supersymmetry, cannot be a function of the phi stars. That is, in complex analysis language, this thing is holomorphic. Okay? It depends on, if you think of z as a complex variable, it depends on z, but not z dagger, right? So it's a holomorphic function, but other than that, it's very much like our quantum mechanics analog. In fact, the rest of the Lagrangian that invokes this is written like this, plus fi times, and remember, it was the derivative of this that showed up in the quantum mechanics actual bottom line Hamiltonian. If I don't write I mean the collection of all of them, okay? Plus the second derivative, if you remember the quantum mechanics example, there was a first derivative term and a second derivative term. And the second derivative term multiplied some B dagger kind of stuff, this fermionic things. And here it multiplies these fermionic operators. And again, this is the epsilon alpha beta contracted scalar product of two left-handed fermions, right? So plus the Hermitian conjugate of this thing. Okay. Good. So let me add one thing here, and then we can complete it. So here, we can see that this F, this annoying F thing, is kind of a triviality. Again, you'll see why it's written like that conventionally in my lectures. Here, we can you imagine putting all of this in a path integral. This F appears as just a Gaussian integral in the path integral. You can just do it, okay? So just do the Gaussian path integral or complete the square, and you'll see that you can get rid of F and it's potential, okay? So if I complete the square, I'll just get this thing squared. And so it'll give me a scalar potential, which is equal to d phi I w of phi squared. And of course, I is repeated in this square, so it's secretly the sum over I, right? And you'll see this is exactly the form, this w prime squared, just like in the quantum mechanics potential, that it looks like this. But then the second derivative, which was also there in the quantum mechanics example, was multiplying some fermionic operators squared, and that's this term here, right? Now, if you are quickly seen by canonical dimensional analysis, you'll see that W has units of dimension 3. So to be renormalizable, you should at most have cubic interactions in W, right? So if it was cubic and you took a derivative, it would be quadratic. If you squared it, you get 5 to the 4th. That's renormalizable. Anything higher would be non-renormalizable. So let's stick to cubic. That means that this, if you have a cubic W, this is linear in phi, and so it looks like Yukawa couplings of some sort, right? Some scalar time fermion. So this is an interesting world unto itself, even without gauge interactions, in that I get phi to the 4th like interactions, which are correlated. They're not randomly got different couplings. They're correlated with Yukawa couplings in a very special way. That's what SUSY is enforcing, just like in the quantum mechanics example. And then kinetic terms. And of course, once I go to this level, I've basically eliminated, I've done this path integral of the F's. I've Gaussian integrated it, and it gives me, by completing the square, just this, okay? Okay, so this is very much, I hope you agree, very much a kind of natural generalization of my quantum mechanics example. Again, coming at it more systematically, the 22 lectures are good for that. What about gauge interactions? So now I have covariantized these, anticipating that we want gauge interactions. And so there are sort of some terms, maybe I should again cordon these things off. So I'll say it again. Often you will see the superpotential written as a function of this capital phi. For what I want you to do in these lectures, unless you refer back to previous ones, is to think of that wherever you see any function of capital phi, just think of it as just this one component, right? So it's only showing up as a scalar field. But think of this as a formality convention from some other way of thinking. Okay, what about gauge interactions? Well, let me squeeze, so I'm going to, my boardsmanship is not very good. So I'm going to keep the potential down here. I don't have much to write here because you're not surprised if I have gauge fields. I need some G mu nu squared, right? Let's leave it at that. And I'll have to have some gauginos, right? These are collectively called the gauginos, right? The Bino, we know, or whatever this general gauge theory might be, renormalizable field theory might be. There's some gauge fields collectively, and they're non-abelian or abelian kinetic terms. There are the gauginos, which would have in whatever their adjoint representation is, just they transform the same adjoint representation as gauge fields. And so you have their Dirac, chiral Dirac operator. And there happens to be a auxiliary field for these. So if A is representing the gauge generator, there's one per gauge field. There's an auxiliary field here. I need to square it, okay? Good, so there's this, and again, this auxiliary field, really a nothing. I'm gonna get rid of it at the end, but it couples, just like this term here. The auxiliary field shows up linearly, multiplying a kind of scalar current under the gauge group. Okay, so this is the generator of the gauge group, like a Pauli matrix for the group SU2. This is whichever species as usual, and it's phi dagger phi. So if you think of this as a row matrix, and this is a column matrix, and this is the square matrix in between, and then contracting the A's, okay? So again, if I just complete the square, you just get another contribution to the scalar potential. And it's usually called the D-term potential, whereas this is usually called the F-term potential for obvious reasons. But let's just write it down. It looks like G squared over 2, and then it's this factor phi dagger I, TA phi I, summed over I, and then the whole thing squared, okay? So that's it. This is secretly supersymmetric, okay? So it looks like an ordinary theory, but there are some correlations that the potential has not got some random couplings. It's got things that are correlated with either gauge couplings or you correlated with the Yukawa couplings in some way. But it has all the magic of supersymmetry hidden in it. So let's specialize to the real world, or at least the MSSM part of the real world, or in the standard model. And so we can ask, like with the standard model, with that particle content, you more or less can see every step of what we're supposed to do here. Like this is compactly telling you everything you need to know by just considering the different species phi I as the different scalars. Squarks and sleptons are those phi's, et cetera, right? So it's easy to see that. The only thing we don't know is what is W, just like in my quantum mechanics example. What is W? Tell me W, we're done, okay? So that's the only thing I have to specify. And we can deduce what it is because these W's better be giving us the standard model Yukawa couplings, okay? So there's at least a minimal W that we need. So the W of the chiral superfields of the MSSM. Okay, I've written it in this formal language, but everything should be interpreted only in terms of the scalar components of these superfields. Well, it should be gauge invariant, like everything we're doing here in gauge theory. And we want Yukawa coupling. So you can see that the easy thing is that there's some Yukawa matrix. Now I have to use I and J over and over again to mean different things. Here it's just all possible species. Here it's the 3 generations, okay, to get Yukawa matrices. So these are the 3 generations of a Yukawa matrix, up-type Yukawa matrix. And it should be something that connects right-handed up-type quarks to left-handed quarks, or electroweak doublet, electroweak singlet, and there should be some Higgs. Now, I've written everything capitalized, and I told you, just interpret it as the lowest, the scalar. This is, in other words, this is like the squark. This is like or anti-squark because it's conjugated. This is a squark. This is the Higgs boson. the reason for writing it like this is that's how you would see it if you either read my previous lectures or change notation and read any, but I need to review, okay?
Raman, you want an I on your upside plot?
Absolutely, thank you. Yes, thank you. So this is of generation I, generation J. As you know, Yukawa couplings generally mix up all the generations in some interesting way, which is part of the fascination of flavor physics, because that it has physical effects. And then there is similarly the down type guys, IJ, DR, I. And now here's where the holomorphy comes. You might say that's a detail. And okay, fine, in my zeroth order take, that's a detail that it's holomorphic. But here, the one place the detail matters. If I have, normally when you write the Yukawa, if you write this, this looks like standard model Yukawa couplings where these are fermions and this is a boson, right? But normally, it's the same Higgs here and here. You recycle the Higgs here by taking its Hermitian conjugate, switching, putting in some signs and switching up and down, and that's called this. That's the standard model. If you don't remember it, review, right? Here, I'm not allowed to take these guys. Forget, I can juggle components, I can put signs in, but what I am not allowed to do in putting this is taking complex conjugate or Hermitian conjugate. Why? Because of the holomorphy rule. Now, that's handy, right? So what I really need is two independent Higgs doublets. That's good because for anomaly canceling reasons, I need two Higgs doublets anyway. So this prime is a really H up and H down, right? Which are the standard names in sort of the two Higgs doublet nomenclature. Okay. Now you'll see that you have interesting Yukawa couplings. When I take these two derivatives, if these two derivatives hit the hit these two quark superfields, right? They'll hit those. It'll leave something in this guy, which means that this expression here will be linear in a Higgs. And it will multiply the fermions of the things I took derivatives with respect to, otherwise known as quarks. So you see that when these two derivatives hit these two fields, I get a standard model Yukawa coupling, right, with fermionic quarks and bosonic Higgs. However, I can take derivatives in all possible ways because I'm summing over all the i's. So I'm going to have many other types of exotic Yukawa couplings, as well as this, okay? And I see in my notes, I was stupid, I forgot one more term here. So which you might have anticipated, but let's just write it. G phi I dagger. It's the SUSY analog of a gauge coupling, lambda A, okay. So normally a gauge field connects the particle and antiparticle of, say, a fermion. Sandwiched in between it is the gauge generator, right? This is normally a gauge field couples to the gauge current. But here, the current is not the usual psi current. It's a current made out of a scalar and a fermion because this is not the usual gauge field. It's the superpartner of the gauge field. But the coupling is the same by supersymmetry. Okay, so sorry, this is, might have anticipated this, but definitely it is there, okay? Okay, so we have a bunch of exotic Yukawa couplings. Like this, technically, is a Yukawa coupling. There are two fermions and a scalar. Here, I get the standard Yukawa couplings if I take the derivatives with respect to these two terms here. But if I take it with respect to these two, I get something involving a squark coupling to a quark and a Higgsino. And so you can play it all out and work and see all of these different things. In general, if you turn it into a bunch of Feynman diagrams, you'll get interesting things that you know already, like gauge fields coupling to scalars. You'll get gauge fields coupling to fermions, like you do in the standard model. and you'll get non-abelian gauge couplings as you do in the standard model. But you'll also get other things involving the superpartners. So this fermionic solid line, right? Fermions are solid lines, scalars are dotted dashed lines. This fermionic solid line on top of a gauge field curly line is what we use for gauginos, right? They're both fermionic and gaugey, right? So there's going to be things like this. And there's the analog of this diagram here, which is okay, this thing. This is sort of the superpartner of this kind of interaction, or this kind of interaction. It hedges between these two and does this, okay? And of course, there are scalars, self-interactions sitting here, things like that. So everything, I think, falls into one of these categories. Like, there will, so one of the references, the classic references, again, it's referred to in my review, is the MSSM primer, whatever you say, depending on where you're from, by Stephen Martin on SUSY and the MSSM, and he would give you all of the Feynman rules and so on, but in a compact way, I've told you. Okay, this is it. Great. So why is this interesting from our bird's eye view? Yeah. Sorry, say that louder. Yeah, so I'm coming to this. Okay, so the question was, is there more I can write in the super? I wrote them to guarantee that I could get at least the standard model Yukawa couplings out, okay? And in a way, for where we're headed, I want to keep it at that minimum, but let me say the answer to your question was, what gives you the right to decide that I'm keeping the minimum thing, right? So it turns out that you could have added more exotic things which come with their more exotic Yukawa couplings, sometimes so exotic as to be dangerous experimentally, right, or dead experimentally, which are things like, so we could have had superpotential terms. Now that these are these colored fields are really have scalar bits to them, right, or we write things in terms of superfields, you can actually write a color singlet superfield that looks like things that look like this, where the color index, what should I call it? I'm using I for so many things. What's another alphabet? A, I'll use capital A. A, B, C. These are color indices, and you can connect them to be a color singlet, like the way you make baryons in QCD using the color. So they're weird things like this that you can write down. And you say, well, it's allowed. Why shouldn't I do it? So we can impose symmetries and conventionally, and by the way, actually allowing them is interesting and possible. So I don't want to make an absolute statement. But one of the simplest kinds of models of this type is to impose symmetries that kill these, okay? And certainly makes discussing the story quicker, faster. Kill these by imposing a symmetry. As I told you, this is the way we hook up color to make baryons. In fact, this thing carries baryon number. It is a baryon. So we can, if I just impose baryon number as a symmetry, then I can kill this. Similarly, there are things that have net lepton number, and I can kill them by imposing lepton number symmetry. There is a fast way that in supersymmetry people kill all of these exotic things that I don't want to talk about, although they're interesting in their own right. And that is, instead of talking about baryon and lepton symmetry, they impose something called R parity. And R parity is just a Z2 symmetry where all standard model fields are even, and all superpartners, the second column there, are odd. Okay, so that turns out at the level that we're talking about to be equivalent to throwing out many of these exotic trilinear couplings in the superpotential. However, that still leaves hanging the question that was asked. There's one thing that has not been killed yet, and that is, since for anomaly cancellation, these two H's, thought of as both left-handed spinners, should have conjugate quantum numbers to cancel anomalies. That means that there is a term that looks like this, H up, H down. Okay, notice again, it is holomorphic. I'm using H, not H dagger, H down. But they have conjugate quantum numbers, so you can hook them up like this and get something quadratic, which when you look here, take two derivatives, you get just a constant, and whatever it multiplies would just be the Higgsino. It would be like a Higgsino mass term. Now, a Higgsino mass term is a good thing, because we haven't seen Higgsinos being massless at colliders, right? So it's a good thing to have, but for the purpose at hand, I want to kill it, okay? I'm still trying to, I'm gunning for the far left cartoon. Okay, everybody's massless by symmetry. So I want a symmetry to just kill this for the moment. And there is a symmetry that kills it, because now I have chiral, if you like, right? This term turns here into a Higgsino mass term. And I have a symmetry that controls Higgsino mass, just like I have a symmetry that controls the electron mass. It's called chiral symmetry, okay? So if I have the symmetry, this symmetry can be forbidden, or sorry, this operator can be forbidden by the symmetry under which H up goes to e to the I alpha H up, and H down goes to exactly the same, e to the I alpha H down, okay? If you think of this as H, and this is sort of, well, you can see that this thing doesn't, if you have a symmetry under this symmetry, this group, then, which is called Peche-Quinn, because it's very closely related to the original theories of axions of Peche and Quinn, couched in the two Higgs doublet model. So this is called a Peche-Quinn symmetry, but it's basically a chiral symmetry that kills this, just like U1 axial kills the electron mass. And if it's broken by a small amount, like in my example yesterday where it was broken by a non-perturbative effect, then the electron gets a tiny mass. So similarly here, we're going to take the extreme limit for now and just say Peche-Quinn, boom, completely tells me I don't have to write this term. But you see now, this theory looks like it doesn't have any explicit masses. Just take a look. There's nothing expanding. So just imposing symmetries, which I couldn't do in the standard model because the Higgs potential didn't have any symmetries that forbid it or suppressed it or controlled it in any way. But here, just by imposing symmetries, everything here looks massless, right? So let's keep going based on that, right? And see just what the next move is. Is it really massless? Well, one, we could worry about non-perturbative effects, et cetera, et cetera. But indeed, the strongest force here is QCD if we apply this to the standard model. And we know that's too piddling. QCD is qualitatively very interesting, quantitatively not what we want in the real world to get TV masses. But let's see if it's really massless. So for that, we really need to work on the Higgs potential. So now I'm using this. So I'm using curly H or calligraphic H to be the superfield Higgs. But I'm just talking about the regular scalar potential based on just these scalar fields here. Okay, so that's these guys. And now you see that if I just stick to just the Higgs, like throw out all the other fields, right? Then actually these would not matter, right? I'm just trying to do a simplified analysis. You could do a better one. In fact, you see that the Higgs then doesn't appear, like the Higgs is not going to show up here, okay? Because it'll always get multiplied by these other guys, and I'm ignoring them, okay? I'm just saying, they're not interesting. One should actually be more careful, but I'm just trying to give you the spirit of what's true. So I'm not looking at that. And here, however, there is a D-term potential for the Higgs, and it looks like contributions from both from the weak SU2 and hypercharge, and it looks like G2 squared plus G hypercharge squared over 8, and here I'm going to just look at the neutral part, because I want to be careful about the Higgs that could get a VEV and break electroweak, okay? As we know, just because you don't see certain masses in the Lagrangian doesn't mean they're not there if somebody gets a VEV. So let me focus on the most obvious VEV that you would worry about, which is the electroweak breaking VEV that preserves electromagnetism. So I'll just look at the neutral components. Again, one should look at all of them just in case some weird thing happens, but I'll just look at the neutral components of these two Higgses and look at this potential. And it turns out to look like this based on that formula. It just looks like this. Okay. Now, that certainly doesn't look like what I wrote there. I'm just saying that if I write this potential where these are the Pauli matrices of SU2 or just the charges of hypercharge, if I do that and rearrange components and just see what's left standing when I only keep the neutral components, you can write this form. Okay, so I'll leave that as an exercise. You play around with it and just do it yourself. But I can write it in this form. So this is the D-term potential that survives, okay, which is the entire potential in this approximation. So now you see, do I have electroweak symmetry breaking or I don't have electroweak symmetry breaking? It's actually very interesting because there's a valley in this potential, which is usually called in the language of this field a flat direction, which we can sort of plot. This is a complex field, this is a complex field. But you can see, I can live at zero energy. By the way, this zero energy is, you might say, what about radiative corrections? Radiative corrections cancel in the same way that they did in the vacuum energy of my harmonic oscillators. They give me zero energy, because zero energy is the supersymmetric limit, right? Q squared is the Hamiltonian. If Q annihilates the vacuum, if you have supersymmetry and Q annihilates the vacuum energy should be zero. So the fact that the vacuum energy is zero is not a surprise. It's what we expect from supersymmetry. What's a surprise is that it's zero, not at one particular value of the field, but along a whole valley of that. And we can sort of plot that like this, that if this is V, and this direction is sort of H up naught equals H down naught, it technically times a phase, right? Because it's only the absolute value. And I can't, so that's really, this flat direction is really a complex space. But let me schematically not draw that. What we have is a potential that looks just like that, right? So what is the vacuum? Well, the potential doesn't tell you. It could be here. It could be any scale you want, in which case I break electroweak symmetry at that scale. So that would be V weaks. And actually, despite appearances, particles would get mass, like fermions would get mass through the VEV of that scalar field. Not quite the cartoon on the far left. However, there is one option. It is possible to actually have zero VEV, which, in the standard model Lagrangian, the standard model potential, if you're given the potential, the VEV is determined. Here it's not determined. I could actually live here, right? So there is actually a solution to the theory, a ground state of the theory, already. Oh, Lagrangian. But there is one option in which the world just looks like this, right? And And indeed, but there are these annoying things. Okay. Now, this was only meant to be a cartoon. We're ultimately headed here. So what I want to say is that in the cartoon, if there's anything that's going to lift this potential, if there are any corrections to this supersymmetric limit, a very idealized world, very rich, but it's possible that the more symmetry-preserving vacuum, that, if this potential changed ever so slightly, I might actually end up here. Okay? So the smallest things can allow me to live here, in which case the world would look like the thumbnail sketch of the universe that we see, the far, far left. So I'm going to go with that I'm allowing myself to choose this particular vacuum. It's an allowed vacuum. And at it, we have achieved a theory in which there's supersymmetry, relates scalars, which don't have any chiral symmetries that act on them, to fermions on them, and with a symmetry like this that we can impose. By the way, you may wonder, if I impose these kind of symmetry transformations, then these terms violate it, but just leave it as an exercise. You can choose Peche-Quinn rotations of these different fields such that these are invariant, okay? So that's an easy thing for you to do. Okay, now, as we get close to the end of today, I wanted to just prepare us for tomorrow with with adding non-normalizable interaction. Okay, yeah.
So is it possible that instead of implying both Peche-Quinn and arterity, the implying this kind of zeta symmetry accidentally can give rise to, like, is there any possibility that I choose the charges of either U or Q in such a way that accidentally Peche-Quinn arises and I don't have to imply it explicitly?
You want other symmetries that?
No, I just want R parity.
Yes. So R parity by itself does not H up, H down. Sorry. Yeah.
But can there be scenarios that accidentally Peche-Quinn is there?
You can have scenarios in which Peche-Quinn is an accidental symmetry. In fact, something like that is what I'm working on, but it involves, to see the accident requires some rather non-trivial dynamics. Either the cheap way, where you use extra dimensions as a very clever, perturbative way of getting very non-trivial things to happen, or strongly coupled physics, either of which I can answer. Say, without imposing it as a symmetry, can be. Okay, what should I say? Let's move this up. Since I'm running out of time, I'll just use this bottom board. So clearly, the story that we've ended up with is not realistic. By the end of lectures, I want to have a realistic theory like this, right? So we are going to need, in what we're doing, this is not essential, but for the simplest model, so you get the entire construction in one set of courses, one set of lectures, I will need non-normalizable interactions, okay? Why? Because I just made a big lecture about how non-normalizable interactions are only useful over some small range, and where am I putting in the non-normalizable interactions? I'm going to put them in at the scale which you would expect non-normalizable interactions to minimally come from, the Planck scale. Higher dimension operation by the Planck scale, which is pretty suppressed. So you should ask, why is something that should have just been important around the Planck scale going to matter to us little fleas living down here, right? So that's because A renormalizable theory like the standard model can reduce to a non-renormalizable theory. That's true. But also the reverse. A non-renormalizable theory can to a renormalizable theory. And it's the simplest example is, suppose I wrote this non-renormalizable, it's in a generic field theory. I wrote this scalar squared Fermi, which is operator, divided by some scale of order the at low energies, who cares, right? That's not happen. For example, suppose I were to tell you that not too far, maybe 7 orders below the Planck scale, this scalar got a VEV. Then all of a sudden, this would be a mass for this fermion, which would be extremely relevant. 7 orders of magnitude below this scale would still give me 10 to the minus 14 Planck mass for this guy, bigger than any. So this is a qualification to what I said about non-normalizable interactions. This is the kind of qualification that's about to hit us. Okay, so it's important. I've run out of time. So next time, we're going to include in that kind of construction of the Lagrangian the most important non-renormalizable interactions, because we're going to need to connect the physics here to something that non-perturbatively breaks supersymmetry and triggers a set of interesting events, one being electroweak symmetry breaking, and gives us a spectrum that looks more realistic. Okay, so next time.